Okay, so question 7. Actually, I think we've seen this question before. So question 7 says, it is known that 5% of the population suffer from a particular disease. Now, the test for this disease has the following characteristics. So we know that if someone has the disease, the probability that the test is positive is 90%. And if somebody does not have the disease, the probability that the test is negative is 80%. Find the probability that someone who tests positive actually has the disease. Obviously quite topical at the moment, particularly to do with sort of testing of coronavirus and bits and pieces like that. There's been a lot of debate about the efficacy and the sensitivity versus specificity of it. So let's suppose that we've got some particular disease where 5% of the population suffers from it. Okay, how are we going to go about doing this? Any suggestions? Good, draw a tree diagram. Okay. So let's start off by drawing our tree diagram. So in this case, the first set of branches, what are they going to build about? Yeah, good. These are all going to be about the disease. We're not talking about the test yet. We're talking about whether you actually have the disease or not. So, okay, let's call D for disease and D dash for not having the disease. Okay. So if it affects 5% of the population, are you happy 5% has to go up here? There's a 5% chance you have the disease, but clearly a 95% chance that you don't. Okay. So the next two paragraphs then, or the next two sentences rather, are going to help us to determine what comes next. So if I just follow on a couple of branches from each of these, okay, what are these two branches going to be talking about?
Positive or negative test result.
Yeah, good, it's going to be talking about the test results, so whether it's positive or negative. So I'm just going to put P and N. In fact, I'm going to put POS because I'm going to be doing probability, so I don't want to confuse it with that, okay? So positive, negative, positive, negative. Okay, so help me out then. What's the probability that's going to go along the top branch? So this one here. So this is the probability that you have the disease. So given you've got the disease, what's the probability that it comes out as positive? 90%. Good, that's what we're told. So it's 90%, which means what is the probability that goes here? 10%. Just 10%. So there's a 10% probability that even though you're positive, even though you have the disease, you come out as negative, right? Okay, what's the probability that's going to go here?
So, positive 20%.
Good. And negative?
3.
Excellent. Okay, so just literally reading that second sentence, which says, if you're negative, the probability that you, or the probability you don't have the disease given it comes, sorry, let me read that again. The probability that you're negative given that you don't have the disease is only 80%. Okay. So we need to find the probability that somebody who tests positive actually has the disease. So what is this question asking? Just give it to me in everyday terms. What is this question asking?
I want to see the ratio of real positive tests to the total number of positive tests.
Okay, good. So in other words, you want to find the probability that someone who tests positive actually has a disease. In other words, you want to find the probability that you actually have the disease given you test positive, right?
Yeah, I didn't word it for, but
Yeah, okay.
I'm looking at what we're looking for. I'm talking about what we're looking for.
Yeah, exactly, yeah. So we're looking at basically, okay, you've tested positive. Now what's the probability you have the disease given the characteristics of this particular test, right? So how could we do that?
In this case, we need to find out all the positive tests, the probability of getting a positive test, regardless of having the disease or not.
Yes.
So in this case, it would be,
Well, that will be part of it, so we'll do that in a second, definitely. So can you remember there is a formula named after Bayes that will help you out? It is in the formula sheet. Yeah, it's in the formula sheet as well.
Something with it and then
Yeah, the formula in the formula sheet, let me just write it down because I know that you've got it there, is the probability of an event A happening, given that an event B has already happened, should be equal to the probability of an event B happening, given that an event A has already happened, times by the probability of A happening, all divided by the probability of event B happening. Okay, so that is in the formula sheet, so you can copy that down. That will help you when you're kind of figuring out what needs to go here. So can you read out what goes on the numerator?
The probability of being positive, knowing if you have
Yes.
disease.
Good. So in this case, A is our disease, B is being positive, based on that formula. So what are you going to multiply by here?
Probability of having the disease.
Good. Probability of having the disease divided by?
Probability of being positive.
Perfect. Okay. So yeah, when you're saying let's find out the probability of being positive, that is part of the formula, right? That is part of it, so we can do it.
Yeah, I like being holistic.
Yes.
Big approach.
Yeah, definitely.
Find things easily.
Sure.
Right, but I agree with that.
Yeah, totally. It will still get to the same answer. And of course, remember that the way that this comes about is just simply thinking about the probability tree diagram, right? It's basically the idea that this times this should be the same as this times this, right? And that was literally how we derived that formula. All right, fine. But let's actually find each of these component parts then. So what's the probability of testing positive given you have the disease? What probability would I be looking at on this tree diagram here? So what's the probability of testing positive given that you've got the disease?
So you go straight up.
This one?
Right
Yeah.
to the top.
Absolutely. So yeah, I'm looking for the probability of testing positive given that I've already got the disease. It's not given that I've not got the disease. I'm giving you the fact that I have the disease, so I have to be here, and then I test positive. So therefore that probability has got to be 90%. Now I'm going to multiply that by the probability of actually having the disease. Yeah, that's just 5%. Yeah? Now this one's going to be a little bit more involved. Probability of testing positive. Well, this kind of comes back to what you were saying, Jean-Sebastian, which is the probability of testing positive is not necessarily, we need to take into account both cases. So whether we've got the disease and test positive, or whether we've not got the disease and test positive. So thus, in order to work out those two probabilities, would you be happy we just multiply the probabilities on the branches together? Okay? So if you take the 5%, the probability you have the disease, and then the probability that you test positive given that, then that's going to be 5% chance times by the 90% chance that you've got of testing positive. Yeah? So it'll be 5% times 90%. So that's what's going to go on one side of the numerator. So 5% times 90%. Okay? And then if we extend that, the other way of testing positive is not having the disease, which has a 95% chance associated, times by the probability then of testing positive given that you don't have the disease. So it's going to be 95% times by the 20% chance of then testing positive. Yeah? So are you happy that we can combine these two probabilities with an add? Because it could be this way or this way of testing positive. So in probability, if it's an or, if it could be this situation or this situation, we'll have to add them. Yeah? So we'll add on 95% times by 20%, like so. Let me just stick all that in a calculator and see what that comes out as. So I'll stick it over here on the right hand side, like that.
Yeah.
Okay, great. So that's about a 19% chance. Okay, so I'm just going to write it across here. It's about a 19% chance. So that's quite low, actually. If you think about it, I'm literally asking the question, well, what is the probability that I have the disease, given that I've tested positive? Right, I go to the doctors and I have this test, comes back as positive, and you go, oh no, my life is over, etc., etc. But actually, there's only about a 19% chance at that particular point. And actually, this is the reason why. I mean, they actually did sort of a similar kind of test experiment, whatever you want to call it, to see what doctors thought of this as well. They said, well, okay, same situation. This is the probability of having the disease. This is the probability of testing positive, etc., etc. This is the accuracy, and they kind of said pretty much the same thing that we were thinking of, which is, well, actually, you've tested positive, and that's a pretty bad thing in life, right? You test positive for a disease, but actually, there is a pretty low probability of you actually having the disease, okay? Yeah, I mean, just to kind of give you a bit more background on this situation, the reason why it's so low is because the disease actually has a fairly low prevalence in society. If this disease had a higher prevalence in society, then if you were testing positive, then you'd have a much higher chance, right? So yeah, the lower the prevalence of the disease and you test positive, the lower that probability is going to be. Hence the reason why you need to do more tests, just because you can't rely on this one.